So we were discussing about the parallel operation, and let us consider the case when the voltage ratios are not exactly equal of the primaries and secondaries of the transformers. In that case, the values of EA and EB will not be equal. EA and EAB not be equal, so that we cannot join these 2 points. And so, if you connect any load impedance Z bar, the total current delivered will be I bar, and it will be shared like IA bar and IB bar as shown in the diagram. Now, how to tackle this situation is that you simply write down the KVL equations in the 2 loops. V bar is the terminal voltage across the load. Therefore, EA bar, as you can easily see, will be simply equal to V bar plus of IA bar into ZA bar. Okay, the series impedance. Similarly, EB bar will be equal to V bar plus IB bar into ZB bar. Okay, so from these two equations, 1 and 2, you can substitute for V in this fashion, that is EA bar is equal to I bar Z bar, where Z bar is the load impedance, I bar is the total current, plus IA bar into ZA bar. And for this one, I bar, you can write IA bar, simple just mathematical treatment, into Z bar plus IA bar into ZA bar. Therefore, EA bar can be written as, if I am wrong, please correct me, Z bar plus ZA bar into IA bar plus of Z bar into IB bar. Similarly, EB bar. So this will be using, this is one equation. EB bar will be similarly equal to I bar Z bar plus of IB bar ZB bar, where you can once again write for I bar as IA bar plus IB bar into Z bar plus IB bar into ZB bar. This can be written as Z bar into IA bar plus of Z bar plus ZB bar into IB bar. This will be EB bar. Therefore, from these two equations, IA bar and IB bar can be calculated in this way. So IA bar will be equal to the impedance matrix, that is this equation you consider, not this one, and this equation. 2 unknowns, 2 equations. So IA bar will be equal to this matrix here, Z plus ZA, and here Z plus ZB, all are bar, and then here it will be Z bar, here it will be Z bar, and the column of this first column is replaced by, when you are trying to calculate this one, it will be like this, and this will be Z bar plus ZB bar. I will be doing very quickly, these are very simple things. So this one, if you calculate, this will be EA bar into Z bar plus ZB bar minus of EB bar into Z bar, whole divided by, if you calculate this Z bar square cancels out if you calculate this determinant, and you will be left with ZA bar ZB bar plus Z bar ZA bar plus Z bar ZB bar, like this it will come. Similarly, IB bar can be found out. I am not writing this one. Only thing you can show that as Z tends to infinity, that is when the transformer is under no load condition, this current will, IA bar and IB bar will be equal, and they will be circulating current, they will represent, that you can easily show That is, if similarly Z bar can be calculated, and if Z bar tends to infinity, indicating the open circuit condition, you can easily show that IA bar will be equal to minus IB bar, and that will be the circulating current. In the transformer. So, for a given current, and if you know EA and EB, you can find out how much will the transformer A will share and how much will transformer B will share. Now, apart from this, I will just do another thing which is slightly tricky in the algebraic manipulation. That is, if you look at the first two equations, that is EA bar is equal to your B bar plus IA bar ZA bar that we have seen. In this case, whether it is possible, it is sometimes useful to express IA bar in terms of the total load current I bar. This can be done in this way. That is, these two equations were there, basic equations, B bar plus IB bar, ZB bar. Now, what you do, you subtract these two equations, okay? Subtract these two equations, so that you will be getting A bar minus EB bar as IA bar, ZA bar, minus of IB bar, ZB bar. This you will be getting if you subtract these two equations. In this analysis, what you are trying to do is this, to express I bar, IA bar or IB bar in terms of the total load current. That can be easily done if you do in this fashion. Now, so therefore, what you get is this IA bar, ZA bar to be equal to EA bar minus EB bar plus of ZB bar, IB bar. This is correct. Now, what you do, you add both sides, this quantity, ZB bar, IA bar, on both sides, such that this will, if you add this one, this will become I bar into ZB bar. That is, add both sides this term, so that on the left hand side it will be ZA bar plus ZB bar into IA bar here is equal to this one. Or IA bar will be equal to EA bar minus EB bar over ZA bar plus ZB bar plus of ZB bar by ZA bar plus ZB bar into I bar. See, obviously, if the voltage ratios were exactly equal, then this would have been 0, this term, and this is just the parallel impedance rules that will make sure how much transformer A will carry, ZB bar by ZA plus ZB bar. In the same way, you can show that IB bar will be how much? It will be just opposite. In the same way, if you go, this part will be there, just EA bar minus EB bar by ZA bar plus ZB bar, and plus here it will be ZA bar by ZA bar plus ZB bar into the total current. That is, when the load current is 0, it will be the circulating current, preceded this by a negative sign. Because when this is not there, this circuit is opened, I bar is 0, IA bar and IB bar will be equal and opposite in nature, and the current will circulate here, okay, inside the secondaries. Now, therefore, it is very unlikely that the two transformers will have same voltages, because you are designing the transformer, even if they are manufactured by the same manufacturer. So the question is, how much should we tolerate this difference of voltages? It is suggested that the difference of voltage should not be so high that the circulating current is greater than about say 5 to 10% of the rated current. Are you getting? Suppose the transformer, two transformers you have taken. Secondary is, and you have made them parallel. Secondary side also you have made them parallel. The moment you make them parallel, there will be circulating current here because difference of voltages will be there. That circulating current should not be tolerated beyond a maximum of say 8% say of the rated current. Ideal thing would have been the voltages are exactly equal, but in case suppose there is a slight mismatch of voltage, it is not that you cannot parallel them. You can parallel them, but keep in mind that the circulating current is not exceeded beyond this 5 to 10% of the rated current, because this circulating current will simply add to the copper loss of the transformer and delivering no power to the external circuit. Therefore, what we have discussed so far, that single phase transformers, if you want to, to summarize, if you want to parallel them, the most essential condition that you can parallel them is that the polarities must be correct. That is the first thing. Then impedances should be inversely proportional to their KVAs. As far as possible, you try to meet that. And thirdly, even if the voltage ratios are slightly different, this should not cause a circulating current even under open circuit condition, which will exceed say about 5 to 10% of the rated current. I have written just 8% like that. So these are the three things. And remember that as a general expression, the output power, if you look here in this expression, the KVA output to the load will be how much? See, voltage is V, single phase transformer. So this KVA output to the load will be S bar if I write. It will be V bar I bar. Is not the voltage here, and at that voltage current is delivered to the load. KVA delivered by transformer A, how much it will be? Transformer A winding current is IA bar. What is the voltage here? At which voltage it is delivering? V only. This is V, here also it is V. So it is V bar IA bar. Similarly, KVA delivered by transformer B will be similarly V bar IB bar. Okay. And another important thing you should remember, that it is of course not a must condition, but one should see that the qualities of the impedances of the transformers are same, in order that they will be operating at the same power factor, such that the algebraic sum of the KVAs really become the actual KVA output of the transformer. So, that I discussed, then I told this one. Someone asked me while I led this class that about something, some confusion was there. That I want to make clear. That is, suppose there is what does that mean really? Suppose the impedances angles are different here. Suppose with respect to this diagram, let us assume this is like this. See, voltage ratios are same like that, and this is the load impedance Z bar. This is I bar, and this is IA bar, IB bar. Suppose the magnitude of impedances are inversely proportional to their KVAs. It will ensure what? It will ensure that whenever there is some load current delivered to the load, the currents will be divided in the inverse proportion of their KVAs. That is what we want. That is, whichever transformer is larger KVA rating, it should share more current than the other. That is what we want. But the point is that suppose the rated current of this transformer, suppose IA rated, some figure I am taking, suppose IA rated is suppose some 50 ampere. And not related with the earlier data. I am just telling, suppose IB rated individually, rated current of the second transformer is 100 ampere. What I am trying to tell, when you load, vary this load, and suppose this current is set to 50 ampere here, and this current is set to 100 ampere here. What I mean to say, the current here to the load will not be 150 ampere, because of the fact that these currents will be added at some angle, In order to get 150 ampere at the output, the some currents in the phases, in this particular case, when the impedances are inversely proportional, these two transformers will then become slightly overloaded. Are you getting? That point must be borne in mind, what I want to say. Is that clear to everybody? That is, if you want to take 150 ampere here, then this current ratio will be 1:2, like that. But the magnitude of the current here will be greater than 50 ampere, and this will be also greater than 150 ampere. So total kVA output will be slightly less than the kVA handled by each of the transformers. Of course, that is, this phasor sum has to satisfy. That is, this I bar will become equal to IA bar plus IB bar. That is okay. But transformers will be operating at different power factors. Anyway, this you solve some problems, then you can understand. Now, next point is about whether there will be any additional constraints put on three-phase transformers to be operated in parallel. So far, I have discussed about single-phase transformers to be operated in parallel. We know how to do it. Suppose three-phase transformers to be operated in parallel. Obviously, what you will suggest to operate two three-phase transformers in parallel? First thing, the line-to-line voltage rating should be same. Are you getting? See, primary side you will parallel, secondary side you will also parallel. So, line-to-line voltage of the three-phase transformers must be same. So, line-to-line voltage should be same. Then, of course, for better sharing of kVA, the impedances should be inversely proportional to their kVAs. That comes from the per phase consideration I discussed, how to analyze a three-phase transformer on per phase basis, is not earlier. So that thing also remains, that for better load sharing, kVA impedances of the transformer should be inversely proportional to their kVAs. That is their kVAs, impedance. But important, another additional point you should remember. Can you tell me what in terms of the transformer connection groups? That is, suppose I will ask it in this way. Suppose you have a transformer YD1. Can I connect it in parallel with YD11? In spite of the fact that the RMS value of the line voltages on the primary side and RMS value of the line voltage on the secondary side, they are equal. But will you allow this to happen? Certainly not, because the length of the voltages are same, but they will be shifted. Is not YD1 and YD11. Primary you have connected YY in parallel. And D1 voltages will be how they will be. Suppose this is the primary voltage. Quickly I will draw. This is suppose the primary voltage. This is FS. Or I used to draw like this. Suppose this is the FS voltage. On the secondary side, FS voltage, if it is 1 here, it will be like this. So voltage triangle will be like this. A phase. With respect to the artificial neutral. But in case of YD11 connection, this triangle will be like this. So A, B, C here and A, B, C here, they are shifted. So if you connect them in, try to connect them in parallel, there will be large circulating current, as if you are trying to connect two sources which are not in same phase, same magnitude. Therefore, the additional condition or constant which is put in case of connecting two three-phase transformers in parallel is that they must belong to the same vector group. That is, the three-phase transformers, three-phase transformers must belong to the same vector group. This is very important. Of course, this means that you can connect YD1 in parallel with DY1. That will do. Start delta, let that be start, this be delta, primary be delta, this be star. You will first see whether line voltages are same, not phase voltages, line voltages are same. That you will ensure and see that the shifting of the voltages are by the same amount so that you can successfully parallel them. So this must be understood very clearly. I will give you some problems on parallel transformers later. Now let us go to very quickly to a topic which is called the Sumpner test, and then I will start rotating machine. So Sumpner test. See, we have so far seen the open circuit test on a transformer and short circuit test on a transformer. These two tests we are familiar with. Now, in open circuit test, what you do is this: you apply rated voltage on one of the sides, and other side remains opened. The transformer, what kind of losses will take place under open circuit test? Only the core loss will take place. There will be no copper loss because the current is so small. So that is, so open circuit test if you only carry out, it will only core loss takes place, core loss. Of course, that will be rated core loss, no doubt, because rated voltage you are applying, rated core loss. Similarly, during short circuit test, what you do is this: one side of the transformers is kept shorted, on the other side you apply appropriate voltage so that rated current flows. Okay. Rated current flows means both in the primary and secondary rated current will flow in order to balance the MMF and keep the core flux same. But in that case, what is the loss predominantly takes place? Only the copper loss. Of course, there will be some core loss also, but that core loss is much smaller compared to the copper loss that is taking place because of the fact you are applying very small voltage to circulate the rated current. Flux level will be very small, so copper loss will take place. Now consider a transformer which is now to be operated to supply loads, because we have connected a transformer not to carry out open circuit or short circuit test, to fully operate it at its rated condition. That's why you have purchased a transformer. So when a transformer is in service, how it will be operating? You will apply rated voltage here on one side. You will get somewhat rated voltage here, and you will connect a load. It will deliver rated current. On that condition, the transformer should be operated when it is in operation. So, in that case, when it is operated like this, what do we find? The transformer, inside the transformer, core loss will be taking place at its rated value, as well as copper loss will be taking place. Are you getting? So, both here, when under loading condition, when transformer is operated, that is in service, both core loss and copper loss will be present at their rated values, if the transformer is at their rated values. Therefore, although open circuit short circuit test is important because you can find out the equivalent circuit parameters, but by doing these two tests separately, you really do not know how the transformers will operate when it is fully loaded. So, one way out is to operate the transformer in the laboratory at full load condition. Is not open circuit test you do, short circuit test you do, and also do load test. That is, you really operate the transformer by connecting some impedance here, so that that can fully load the transformers and see your wattmeter readings, ammeter readings, etc., whether the windings are capable. The one point is, of course, very clear that neither the open circuit test nor the short circuit test alone will give you the appropriate temperature rise in the transformer, because other loss is completely absent in either of the test. But in load test that is possible. Both the see, if you connect wattmeter, inside the transformer, both the core loss is taking place and copper loss is taking place. You have loaded it. But the only objection to this load test, what is the objection to this load test? Power dissipation means, okay, perhaps for a very small transformers you can carry out in the lab, say 5 kilowatt transformers, you have a 5 kilowatt load like that. Imagine you have a distribution transformer whose rating is say 100 kVA. I am lower side I am telling only, and suppose its rating is 6000 stroke 400 volt transformers. Okay, in that case, if you want to do a load test on the transformer to ascertain the real life situation in the lab, then you require this sort of voltages to be present. At least 400 volt should be present. 6600 volt will be perhaps induced, and you have to connect a load whose capacity is 100 kVA. And all this you are doing just to test the transformer, and your power, whatever will be consumed, will be just wasted, because for testing purposes. So, all these things can be avoided if one carries out the Sampner test, and at the same time one can get the real feel how the transformer will behave when it will be on full load condition. So, for this, of course, you require two transformers, two similar transformers you require to carry out this test, two similar transformers are needed. That is, voltage ratings and the kVA, they must be similar. And then you connect it in this fashion. Suppose this is the primary of one transformer and this is the secondary of this transformer, and suppose these two are, this is the primary of the other transformer. Okay. So this is suppose transformer 1 and this is suppose transformer 2. These are the primaries. And secondaries I am drawing in this way. This is the secondary of this transformer and this is the secondary of this transformer. And suppose the dots are like this here. Now what you do is this, these two primaries, you connect them in parallel. And here you can connect an ammeter and an wattmeter. wattmeter. And give rated voltage to the primary side. Here you give rated voltage at rated frequency, of course. Now, if you give, then here there will be the induced voltages on the secondary side, whose magnitudes will be equal because I have taken similar transformers. Okay. Now, on this side, the secondaries, you connect it in this way. You take a variac and you connect an ammeter and another wattmeter here and supply it in this way. This is the pressure coil terminal and connect it in this fashion. And initially, suppose you keep the variac at the 0 position, so no voltage exists between these 2 points. Then what will happen is this: if you measured voltage between these 2 points with a voltmeter, how much it will read? 0 it will read, provided these are also dots. So sometimes, suppose without doing polarity test beforehand, you can carry out the test if you remember this particular fact, that you connect arbitrarily these 2 primaries in parallel, and this way you connect and just measure this voltage. What could be the other alternative? It could be twice this voltage will come if the dots are here. Okay. So one way of doing it, you do first polarity test, then correct it, short it out. So what is done is this: there a shorting switch is put and a voltmeter is connected, and seen that this, because circuit will be completed like this via this wattmeter, ammeter, this 0 point initially it will be here, so this voltmeter will read if it is not connected properly. In fact, twice these readings will come. Now after that, what you do, you short this out. If you short, how much will be the current on the secondary side? 0, because suppose initially this jockey is here, so no voltage, resultant voltage will act in this closed path. These 2 voltages will be in opposition. Now what you can do is this: you can slightly apply some voltage from this second source. You slowly increase this variac. So your ammeter will immediately show reading. Obviously, you should not apply such a voltage which will make this ammeter reading greater than the rated current of the secondary side of the transformers. That will be the final point we should go up to. Anyway, you apply some voltage such that rated current flows in the secondary side. It will be flowing like this. Now, then what will happen? How will be the current? Suppose the currents are flowing like this. You apply some voltage. Now, in these transformers, the current will be flowing like this. That is through the dot at any instant of time. Let us see. Suppose through the dot current is coming out. Then this transformer flux will be upset. These are 2 separate transformers. Therefore, the primary will react in which way? By inviting additional current, such that the flux in this core of this transformer remains same. So immediately once this current flows, primary will draw a current like this. So suppose this is I2 and this is I1. Through the dot current will be coming in. Now for this terminal here, for the second transformer, secondary current, see these 2 are dot, means other 2 are also dots. That way if you think, through this current is coming out. Therefore current will, this one is I2 because they are series connected, and this one will be I1 because the transformers are similar, trans ratios are similar, I1. So the current distribution in the secondaries and the primary windings will be in this fashion, like this. Now obviously at these junctions, if you apply Kirchhoff's current law, this I1 will be circulating within these two windings. There will be no branch of this I1 to the supply side here. In fact, initially, going back, when the switch was opened, how much was this ammeter will be reading? When the switch was opened, you have not parallel, not zero, it will draw the sum of the no-load currents. This no-load current, this no-load current. This twice I0 it will draw from the supply. And wattmeter will read what? Twice the core loss. Twice the core loss of the transformer, 2P core. Now, what I am trying to tell, even after you connect the secondary in parallel here, like this, and apply some current here, the primary current will not change. It will remain where it was. Because there will be reflected current on the primary side of both the transformers, but they will be circulating within them. That can be easily seen by applying Kirchhoff's current law at these junctions. Now the question is, what this wattmeter will read? This wattmeter will obviously read the copper loss taking place in the two windings, because rated current is flowing. So equivalent resistance copper loss. So this wattmeter will read 2P copper. And this is, I am passing the secondary rated current, I2 rated here. Therefore, in this test, if you now look as an observer, what is happening? Both the transformers are having full load core losses because rated voltage has been applied. And at the same time, both the transformers are having full load copper losses. So as if this is the situation which you will get if you load the transformer separately with the appropriate load to fully load the transformers. Are you getting? But what is the advantage? Advantage here is how much power is drawn. Of course, two sources are necessary, but how much power totally is drawn to carry out this test? Only the core losses of the two transformers and the copper losses of the two transformers. And you know the efficiency of the transformers are quite high. Those losses only will be very small. In other words, what I want to say, that the transformers will only draw the losses, but to an observer, observer will be feeling that the transformer is fully loaded. What this type of test called? Back-to-back test is okay. Sometimes this type of test is called phantom loading. Phantom, that is something the transformers. Are you getting? So it is similar to phantom loading of the transformers. That is transformers. So naturally, testing transformers. So this way, if you test, you can come out with several things. You can perhaps you can estimate the temperature rise by maintaining the rated current all the time by adjusting it. But you load it for significant time, say over a complete day, you keep it loading. Then the resistance of the winding will change with the temperature rise in the transformers. From the readings of the wattmeters, you will be able to estimate the winding resistance, hence predict the temperature like that. Are you getting? So those things are possible. And also you are testing the transformer, really how it will behave when it will be put in the service. See, during the loading, if you find the windings, whether it is capable of carrying the rated current, whatever has been supplied to us, that also will be well checked without really loading the transformer, but making a scene that it is like loading the transformer, because primary, secondary windings are carrying rated current. Therefore, this testing, Sampner testing assume importance. But only constant is you require two transformers. But that also is really not a constant for the manufacturer of the transformer. Because when a manufacturer is not certainly going to manufacture a single transformer, he will be manufacturing transformers in hundreds, is not, while supplying say one ACB, State Electricity Board. If not 100, 50, 20 like that. So therefore all these transformers can be paired and can be tested like that. Of course in this one. Anyway, you read about this one. Now today I will start briefly introduced about the rotating machine. I will just introduce to you rotating machines. Just you first listen what I am telling you. In rotating machines, unlike transformers, in every rotating machines, whether it is a DC machine or AC machines, synchronous. First I write down the names so that there are machines like DC machine, DC machines, or AC machines. Just AC machines. AC machines can be of various types. Induction machine or synchronous machine. Only this much I will write. These are the most important machines like this. But all the machines, rotating machines, they operate with some basic principles involved. In fact, in all rotating machines, you will find there are two structures will be there. One is called the stator. Every rotating machines. And the other part is called rotor. The name obviously suggests that the part of the machine which will not be moving will be the stator part, and the part which will be moving is the rotor part of the machine. And generally, both stator and rotor will house windings. They will have several coils wound in a particular fashion. So both stator and rotor will have windings wound on those structures, windings placed on stator and rotors. In general, if I draw a cross-sectional diagram, a machine may look like this. Suppose you consider a hollow cylindrical stuff, say made of iron here. This is iron, which has got a length here. Say this is hollow, inside it is hollow, and this rim, that is the thickness of this cylinder, is made of iron. And also not only so, this structure, which is the outer of the machine, is generally the stator, which is fixed. This is the stator of the machine. Now, where the windings will be placed? Generally, the inner periphery of this one will be slotted like this. All along this periphery I am not drawing. Okay, it is slotted. All along the length of the machine, it will be slotted like that. So this is the stator made of iron, and there will be a number of slots along the inner periphery of that thing. Now in these slots will be put your conductors or coils, or that is called the windings. Okay, on the inner periphery of this machine, several sets of conductors will be placed along the periphery. So this part is rotor. So this is the stator windings. Now inside this one there will be another iron cylinder, which is of course not hollow, and it will just inserted inside this one. and this part is the rotor. Obviously, in order that rotor will rotate under the influence of some electromagnetic torque or force, whatever it is, it has to move. It can move only when there exists an air gap between the stator and rotor. So this air gap cannot be avoided. Okay, so this portion which is between the stator and rotor structure is called the air gap of the machine. Air gap. Obviously, rotor 2 will be slotted, the outer periphery like this, so that some winding can be housed on the rotor structure. Okay, so rotor and stator both will be made of iron, and their inner periphery of the stator winding should be slotted, and generally rotor also are slotted, and there will be placed windings on the rotor and stator one, and the rotor and stator will be separated by an air gap. Air gap should not be too large, okay, and at the same time it should not be too small such that it can cause some problem in rotation of the machine. The last point after making I will close today, that is obviously generally the stator structure of these machines or the rotor is not obtained from a solid block of iron. There also stampings are used. In fact, you have several circular plates, thin plates. You keep one above the other and make the length of the machine. I think you have got the idea. That is this one. Or similarly, to avoid eddy current losses in a transformer, they use stampings and they are stacked together. And slot will make that length where you can put the conductors. Okay. So AC machines, both stator and rotor in case of induction machines, they are parallel. So anyway, tomorrow I will continue with this.